The elements which possess partially filled d subshells either in the atomic state or their oxidation state are called as transition elements. The transition elements with atomic number 21, that is scandium to zinc, atomic number 30, and having incomplete 3d orbitals is called first transition series. Coming in this trend, actually the electronic configuration should be argon 3d 9 4s2. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with a new chapter, D and F block elements, that is the fourth chapter of your syllabus. So in today's session, we are going to discuss the introduction, that is where exactly D and F blocks elements are present in your periodic table, right? And then what is called by transition series, then general electronic configuration of D block elements, as well as some characteristics of transition elements we are going to study. Okay, so beginning with D block elements. So if you see the periodic table, you are already familiar with the periodic table. Yes, in class 11 also you have studied, that is in your first PUC also you have studied regarding the periodic table in the chapter classification of elements in periodicity in properties. So in that chapter we have discussed the general properties of the periodic table. Yes, as well as where is S block, where is P block, D block and F block located, right? Now coming on to our chapter, we will be focusing on the D and F block elements. So like how we have studied in last year, the same way we are going to study the details of this D and F block elements. That is, we are going to study the physical properties, the chemical properties, their position in the periodic table, some general physical trends, that is how it will change in a period, in a group, all that we are going to study. Now coming to the periodic table, we already know that the first and second group consist of the S block elements, right? These two are your S block elements, right? Now coming to this side, that is from group 13 to group 18 belongs to the P block elements. Now the in between part, that is group 3 to group 12, this much part belongs to your D block elements. Yes or no? So that is S block, this is P block, and the middle part that you can see, that is the D block elements, right? Now there is one more part, F block elements as well. So if this is S, that is P, and this is D, where is F situated? Yes, F is separately placed below the periodic table, which is having two series. Now this is your F block elements. Right. Now, F block elements is taken out from the D block elements. As you can see here, if we move from left to right, the atomic number should increase. Yes or no? So, you can see here, after 56, you have 57. Right, for lanthanum, the atomic number is 57. After 57, what you can see? 72. Now, where are those elements ranging from 58 to 71? They are not present in D block. From that means after lanthanum, the elements that are coming, they are taken out from here and placed separately, that is cerium to lutetium. That is your F block elements that you can see. That is your 4F elements. What is 4F? We will discuss later. Now coming on to the next part, actinium, you can see the atomic number is 89 and the next one is 104. Right. Now, where are those elements? Those elements are taken from there and placed separately. That is 90 to 103 you have placed separately. So, this is your periodic table. So, now what we are going to study in detail is this D block element and F block elements. What are its general properties? What are its trends in physical properties? What is their reactivity? Any exceptions are there? All of that we are going to study. Right. So, coming back to this, in the modern periodic table, the elements have been grouped into 4 blocks, namely S, P, D and F. Right. So, you can see S is here, P is this, and the middle part is D, and the last part that you can see, that is the F block elements. Right. The elements belonging to group 3 to 12 are called as D block elements of transition elements or transition elements. Right. So, you can see here that is from group 3. This is your group 3 to group 12. This much part is called as your D block elements, or another name is also there, that is transition elements. It is also called as transition elements. Now, what is this transition elements, or all D block elements considered as transition elements? All that we are going to see, right? Now, the elements which possess partially filled D subshells either in the atomic state or their oxidation state are called as transition elements. Elements which possess partially filled D subshells either in the atomic state or their oxidation state are called as D block elements. Okay. Now, why exactly we are calling these blocks as S block, P block, D block, F block? Because the last electron goes to that particular orbital, right? For example, it is called as S block, right? That is all these elements which is present here. The last electron goes to the S orbital, right? Now, coming to P block elements, the last electron goes to the P orbital. Now, here in D block elements, the last electron goes to the D orbital or D subshell. Now, coming to the F block elements, the last electron goes to the F orbital. So, this is how, or that is how the name comes: S block, P block, D block and F block. So, as we are focusing on the D block elements, we already know that the last electrons will be filling into the D orbital, right? I hope that is clear. Now, coming on to this point, what is transition elements, right? Now, are transition elements and D block elements same? So, transition elements, the definition states that these are those elements which possess partially filled D orbitals either in their ground state or in their higher excited states, right? So, they should be always having partially filled D orbital. That means D orbital should not be completely filled. So, how many D orbitals are present in D subshell? We already know that we have 5 D orbitals, right? 5 D orbitals are present. So, partially filled means it can occupy 1, 2, 3, 4, 5, 6, 7, 8, 9. Till 9 electrons, we can say it is partially occupied. Yes or no? Now, if there are completely 10 electrons, that is in all orbitals, 2 electrons each if it is present, then I can say that this is completely filled electronic configuration. If your D block element is having this completely filled electronic configuration, then it does not become a transition element. So, transition elements are those elements which have incompletely filled D orbitals, right? If it is completely filled, it doesn't become a transition element. So, I hope the difference is clear to you. Moving on to the D block elements are called transition elements as they represent change in properties from most electropositive S block elements to least electropositive or most electronegative P block elements, right? So, it is also called as this transition elements. The name calls it as transition elements because there is a transition between the properties. That is, S block elements are generally very high electropositive. They are ready to remove its electrons, and P block elements are ready to gain electrons. They are highly electronegative. So, these D block elements comes in between them. So, that is why their properties will be transitioning between S block and P block. That is why they are called as transition elements, right? Now, copper, silver and gold are transition metals because in their commonly occurring states, they have partly filled D subshells. But zinc, cadmium, mercury of group 12 does not have partly filled D subshell in their elementary or common occurring oxidation state and hence are not considered as transition elements. So, coming back to the periodic table, you can see here this is copper, silver and gold. So, if you see the electronic configuration of copper, silver and gold, it will not have a completely filled D orbital. So, the electronic configuration of copper can be written as argon 3D10 4s1. So, seeing this electronic configuration, you might say that it is 3D10. It is a completely filled configuration, right? D10 is there. That means all the D orbitals are completely filled. You might say that yes, it is not considered as a transition element. But copper is considered as a transition element because the definition states that transition elements are elements which have incompletely filled D orbitals in their ground state or in higher oxidation states, right? So, their common occurring higher oxidation state for copper is +2. So, in that case, 2 electrons are removed means 1 electron will be removed from the S orbital, another electron from the D orbital. Then your electronic configuration becomes argon 3D9. Yes. So, now in this case, is it completely filled? No. So, copper is considered as a transition element. Same goes with silver and gold, right? Now coming on to zinc, cadmium and mercury, that is group 12. Now this is very important. They are an exception. Rest all the D block elements are considered as transition elements, but the group 12 elements, that is zinc, cadmium and mercury, are not considered as transition elements because they have a completely filled d orbital. Now coming on to the configuration of zinc, argon 3d10 4s2. This is the electronic configuration of argon. Now this is in its ground state. The common oxidation state for zinc is zinc plus 2. So in that case also, what will be the electronic configuration? It will be just 3d10. These 2 electrons will be removed from the 4s orbital. Now what happens? The final electronic configuration is argon 3d10. So neither in its ground state nor in its excited state, zinc is going to have a partly filled d orbital. It is going to be completely filled always. So that is why zinc, cadmium and mercury is not considered as a transition element. So this is an exception that you have to remember, that is zinc, cadmium and mercury is not considered as transition elements. So I hope the reason is also clear for you. Now moving on, transition elements consist of 4 rows. These series are called as transition series. So generally we know that the vertical columns are called as groups and the horizontal rows are called as periods, right? So in here we are going to call these periods as series, right? So there are a total of 4 series here, as you can see here, 1, 2, 3, 4, right? 1, 2, 3 and 4. 4 series are there in D block elements. Now coming back, the first series is called as 3D series. That means the electrons will be filled into the 3D orbital, right? The transition elements with atomic number 21, that is scandium to zinc, atomic number 30 and having incomplete 3D orbitals is called first transition series. So 3D series ranges from scandium to zinc, that is 21 to 30. Now 4D transition series, the next one, it consists of elements with atomic number 39 to 48 and having incomplete 4D orbitals. It is also called as second transition series. Next is the 5D series. It consists of elements with atomic number 57, 72. Now that is lanthanum 57, which is actually not an F block element. It is coming under the D block itself. So it ranges from hafnium to mercury having incomplete 5D orbitals, also called as third transition series. Now the last one is 6D. It consists of elements with atomic number 89, that is actinium. Like I said, it is considered as a D block elements. Right. Now, it starts from 104 and ends with 112. Right. Now, having incomplete 60 orbitals, it is also called as fourth transition series. So, as you can see here, there are 4 series. The first one is called as 3D series ranging from, you can see here, scandium to zinc. So, that is the first series, 3D series. Next one is 4D series starting from 39 ending at 48. The next one is starting from lanthanum ending at mercury, right? And the last one is actinium 2. You have the atomic number 112, right? Now the 60 series is still not complete. More elements are still being discovered, right? Now what you have to remember in this chapter is, as I told you, you have 3D series, 4D series, 5D series and 6D series. What we are going to focus is all the properties and the chemical and physical properties of the first series, that is 3D series, scandium to zinc. So if we study that properly and if we remember the electronic configuration as well as the atomic number of each of these elements belonging to the first series, that is from scandium to zinc, we can predict the properties of 4D as well as 5D. So all the properties and the discussions in trends, we are going to focus on the first series, that is 3D series. So I want you all to remember the atomic number of the elements from 21 to 30 with their elements, which are the elements ranging from 21 to 30 and their electronic configuration as well, right? So if you are thorough with the 3D series, the same applies to 4D as well as 5D. Now, coming on to the general electronic configuration, that is what I was discussing from atomic number 21 to 30 we are going to discuss here. So the first element is called as scandium. The symbol is Sc and the atomic number is 21. So how do you write the electronic configuration of this? So it is written in square bracket argon. So argon is the nearest noble gas to this scandium. So till argon, the electronic configuration we need not write, that is 1s2, 2s2, 2p6, all of that is not required to be written. Directly we can write in square bracket argon, meaning that all the orbitals until argon is filled already and it is shown there. Right. Now what is the atomic number of argon? It is 18. So already 18 electrons are being filled. Now the rest of the electrons only I am focusing on. So which are the next two orbitals you are having? It is 3d and 4s. Right, 3d and 4s. Now what you have to understand is, it is written in the form 3d and 4s, not 4s and 3d. It comes from the n plus l rule, which you have already studied. Right, according to n plus l rule, 4s orbital is having more energy than 3d. That is why it is written then after 3d. Now what you have to understand, even if it is written 3d and 4s, the last electron always goes to the d subshell and not the s orbital, right? It goes to the d orbital, not the s orbital. This is what you have to remember, right? It goes to the 3d orbital. So hence I can write the general electronic configuration of d block elements as n-1d 1 to 10 ns 1 to 2. Can I write like this? n-1d 1 to 10 ns 1 to 2. Why it is written n-1? So you can see the last shell which is present is fourth shell, right? But the d orbital is in the third shell, right? So you have to understand this difference, right? This n-1d is called as the penultimate shell. This is not the last shell. This is the penultimate shell, and this one is your valence shell, right? So coming back to this, 4s will be your last shell, that is fourth shell will be the last shell. But the previous one is the third shell in which the d orbital is present. So what you have to understand, the last electron always goes to the d orbital. That is why it is called as a d block element and not an s block element, right? So coming back to scandium, it is argon 3d1 4s2. So 18 electrons are already filled. Then you have 3d orbital and 4s orbital. So after 18 electrons are filled, the next electron will go to 4s, right? As I told you, even if we are writing like this, first the electrons will be filled in 4s, then will come to 3d, right? Because 3d is your last orbital. Fine. Now coming on to 4s, after 18, 19, 20 will be filled here, and the 21, the last electron will be filled in the 3d orbital. So that is the electronic configuration. Coming on to titanium, the atomic number is 22. So you have argon 3d2 4s2. So till argon the atomic number is 18. 18 electrons are already filled. 19, 20 will go to 4s. 20, 21 will be here in 3d. Now coming on to vanadium, atomic number is 23. Argon 3d3 and 4s2. Right, 4s2 will be filled first, then it will come to 3d3. Now chromium is an exception. The atomic number is 24. So coming in this order, what is supposed to be the atomic number of chromium? It is supposed to come as argon 3d4 4s2. Yes or no? It is supposed to come as argon 3d4 4s2, right? You have 3d1 here, 3d2 here, 3d3 here. The next one should be 3d4. But that is not happening. The electronic configuration is argon 3d5 4s1. Now what is this reason? The reason behind this is that the 3d and 4s orbitals are having almost similar energy. So what happens is the electron from s orbital can move to the d orbital. So what happens if one electron moves from 4s to 3d? You will get the configuration as 3d5 and 4s1. Now if you are getting a configuration like this, now you can see it is 3d5. That means you are getting a half-filled electronic configuration. So last year also we have studied, if the electronic configuration is half-filled or completely filled, the element is going to have extra stability. So because of this reason, in the case of chromium, one electron shift from the s orbital to the d orbital. Hence it will get a, yes, you can see 3d5 half-filled electronic configuration. Hence it becomes stable. That is the reason it is an exception. Right. Now moving on to the next one, manganese. Atomic number is 25. So you will have argon 4s2 and 3d5 will be there. Right. Now moving on to next one, iron. Atomic number is 26. Argon 18 is already filled. 19, 20 in 4s. The next 6 will be in 3d6. Now coming to next one, cobalt. Atomic number is 25. You have argon 3d7 and 4s2. Right, nickel, atomic number 28, argon 3d8 and 4s2. Now till here it is okay. Moving on to copper, again it is going to be an exception. The atomic number is 29. Right, so coming in this trend, actually the electronic configuration should be argon 3d9 4s2. Yes or no? But is this happening? The electronic configuration of copper is argon 3d10 4s1. Now how did that happen? As I told you, one electron from the s orbital jumps to the d orbital because their energies are similar. Because of that, it is going to get the electronic configuration 3d10 and 4s1. You can see 3d10 and 4s1. Right. So now, as it is getting 3d10, what you can understand from here, it is going to get a completely filled d orbital. Because of that, the electronic configuration of copper will be 3d10 4s1 and not 3d9 4s2. Right. Now the last one is zinc. Atomic number is 30. It is of course argon 3d10 4s2, completely filled orbitals. Hence it is not considered as a transition element. I hope it is clear. Now this electronic configuration you have to be thorough with. Right. The exceptions also you have to be very careful about. So once you are clear with the electronic configuration, all the answers or all the questions from this chapter will be clear for you. Right. So what you have to understand is the questions from this D and F block elements, the answers of all that questions lies in this electronic configuration itself. So once you are clear and thorough with this electronic configuration, things will be easy for you. Now, moving on to the characteristics of transition elements, except for mercury, which is a liquid at room temperature, all other elements are solid metals exhibiting all the characteristics of a metal. So all the D block elements that you are having, all of them are metals. And whatever properties generally metals are having, they are solids, they are ductile, they are malleable, all that properties these D block elements will be also having, except only one person, that is mercury, which is liquid in state. Now, they show variable oxidation states unlike S and P block elements. Many oxidation states can be shown by D block elements. S block elements generally show only two oxidation states, +1 the first group and +2 the second group. Same way P block elements also do not show a variable oxidation state, right? But coming to D block elements, they show variable oxidation state, right? Now, the discussion of variable oxidation states we will be doing in the upcoming classes. They and some of their compounds shows catalytic properties. Now, I hope you are familiar with what is a catalyst and where it is being used. In many reactions, we use catalysts to increase the speed of the reaction. Now, most of the catalysts we are using in various reactions are these D block elements itself. We use iron, we use nickel, platinum, palladium, all of that comes under D block elements itself because they are having catalytic properties. Their compounds are colored, right? Now, they show colors also. Now, they have great tendency to form complex compounds, right? They form complex compounds or coordinate compounds, and they form alloys and interstitial compounds as well. So, you are already familiar with what is alloys, interstitial compounds also we are going to discuss in this chapter. So, in detail we are going to study what is the reason behind D block elements forms catalytic properties, or it shows color, or why it forms complex compound, why it forms alloys, interstitial compounds. All of that in detail we will study in this chapter. So, in the next session we are going to discuss general characteristics of transition elements starting with atomic radii. So, I hope the concepts that I've covered in this session is clear for you. So, that's all for today. Thank you.